Welcome! In this session, we're going to explore one of the most powerful features of PyTorch, Autograde and gradients. You've already learned how to create and manipulate tensors in PyTorch. Now, we'll see how PyTorch automatically tracks those operations and computes gradients for us. Understanding gradients is essential because they are the key to how deep learning models actually learn, by adjusting parameters in the direction that reduces errors. By the end of this unit, you'll know how to use Autograde to compute gradients, inspect them, and even control when they're calculated. Let's start by understanding what a gradient actually means. In simple terms, a gradient measures how much a function's output changes when its input changes. You can think of it as the slope of a curve at a specific point. It tells us how steep that point is and in which direction the function is increasing or decreasing. In machine learning, we use gradients to guide learning. When a model makes a prediction, we calculate how far off it is from the correct answer. The gradient then tells us which direction to adjust the model's parameters to make the prediction more accurate next time. So, gradients are the foundation of optimization. They help our models learn by following the path of steepest descent, or in other words, the direction that reduces error. Now that we understand what a gradient is, let's see how it's used in machine learning. When a model makes predictions, we calculate how far off those predictions are using a loss function. The gradient tells us how that loss changes when we adjust the model's parameters, for example, the weights in a neural network. Optimization algorithms, such as gradient descent, use these gradients to update parameters in the direction that reduces the loss. Step by step, the model moves downhill on the loss curve toward the lowest point. That's where performance improves and learning happens. In short, gradients are what allow machine learning models to learn from their mistakes. When we work with PyTorch, one of its most powerful features is how it automatically tracks all operations performed on tensors. This tracking mechanism is known as Autograde, short for automatic differentiation. Let's take a closer look at how this works, step by step. In step 1, PyTorch builds something called a dynamic computation graph as operations occur. Every time you perform an operation, like addition, multiplication, or even a complex neural network layer, PyTorch records it as a node in a graph. This graph connects the input tensors, the mathematical operations, and the resulting outputs. The word dynamic means that this graph is built on the fly, while your code runs. You don't have to define the whole computation beforehand, and that makes PyTorch flexible and very Pythonic. In step 2, each tensor that's created through an operation automatically keeps track of how it was created, through an attribute called grad_fn, or grad function. For example, if you multiply a tensor by 2, PyTorch attaches the tag mul_0. If you add something to it, PyTorch marks it as add_0. These gradient functions act like breadcrumbs, showing PyTorch how to retrace its steps later when calculating derivatives. Finally, in step 3, this graph of connected gradient functions allows PyTorch to perform automatic differentiation. When we call the dot-backward method on the final output tensor, PyTorch walks backward through this graph, from the output, through all the operations, back to the inputs, and computes gradients automatically. This process is called backpropagation, and it's the foundation of how neural networks learn. In summary, Autograde is like a built-in notebook that remembers every computation. It builds a dynamic graph as you work, records the function that produced each tensor, and uses that history to automatically compute gradients, saving you from doing the calculus by hand. In PyTorch, we often need to decide which tensors should be tracked by the automatic differentiation system and which ones should not. This control is handled using a property called requires_grad. When a tensor is created with requires_grad equals true, PyTorch starts tracking every operation performed on it. This means that later, when we call backward, PyTorch will know exactly how to compute the gradient for that tensor. In the code shown here, we create a tensor x with requires_grad set to true. Then we perform a simple operation, squaring it to produce y. Because x is being tracked, the resulting y will also be part of the computation graph. If we check y dot requires_grad, it returns true, confirming that PyTorch is watching it for gradient computation. Now look at the next block. Sometimes we want to perform calculations that don't need gradients. For example, when evaluating a trained model or processing data. In those cases, we can temporarily stop gradient tracking using torch.no_grad, parentheses. Inside this block, PyTorch suspends Autograde, so operations are faster and memory usage is lower. When we create z inside this context, z.requires_grad is false. That means z is treated as a constant. It won't be included in the backward pass. So, to summarize, use requires_grad equals true when you want PyTorch to learn from a tensor. Use torch.no_grad when you just need to calculate something without updating weights. Managing this correctly keeps your code both efficient and easy to debug. In this example, we'll see how PyTorch automatically computes gradients using the backward method. Here, we first create a tensor x with requires_grad set to true, meaning PyTorch will track any operation involving x. Then, we define a simple function, y equals x squared plus 2x plus 1. When we call y dot backward, PyTorch automatically traverses the computation graph it built earlier and calculates the derivative of y with respect to x. It then stores that result in x.grad. If we print x.grad, we get 8.0. Because the derivative of this function, dy by dx equals 2x plus 2, and when x equals 3, that gives 8. So, the backward method is what triggers automatic differentiation, and the gradient can always be accessed through a tensor's.grade attribute. This process is the foundation of how neural networks learn, by adjusting parameters in the direction that reduces the loss, based on these computed gradients. Let's walk through how PyTorch handles gradients during training. When we perform backpropagation using the .backward function, PyTorch automatically computes and stores gradients in each tensor's .grad attribute. However, these gradients don't reset by themselves. They accumulate after every backward call. That's why, in a typical training loop, we must clear the gradients before computing new ones. We can do that using x.grad.0_ command for a single tensor, or, more commonly, optimizer.0_ command when training a full model. In this example, we first calculate the gradient of y equals x squared with respect to x, where x equals 2. The derivative, dy over dx, is 2x, which gives us a gradient value of 4.0. Next, we reset the gradients using x.grad.0_. When we check again, the value becomes 0.0, meaning the tensor is ready for the next backward pass without carrying over old information. Finally, we demonstrate the detach method. When we call x.detach, PyTorch creates a new tensor that shares the same data but is disconnected from the computation graph. This is useful when you want to use a tensor's value, but stop tracking its gradients. For example, when evaluating a model or exporting results. In summary, .backward command computes gradients, .0_ command resets them, and .detach command stops tracking when you no longer need gradients. Managing these steps carefully ensures your training remains stable, efficient, and mathematically correct. That brings us to the end of this session on Autograde and gradients in PyTorch. We explored how PyTorch automatically builds and tracks a dynamic computation graph, how .backward computes gradients, and how to manage gradient tracking effectively using tools like requires grad, no grad, and detach. Take a moment to review the examples and make sure you understand how each part connects. If you have any questions, please post them in the discussion forum or bring them up in our next live session.